Welcome back to the Chem OG. Today's lesson is about chirality. Chirality has to do with symmetry or lack thereof. So a chiral object is one whose mirror image is not the same as the original. And the word chirality comes from the Greek word for kyria, or the Greek word for hand. And so the reason that we talk about chirality with respect to the hand is, amazing as they are, when we take a look at our hands, our left hand is the mirror image of our right hand. Okay, so if you put them both in front of you like this, you'll find out they're mirror images of one another. But the interesting thing about our left hand and our right hand, even though they are mirror images of each other, they are different objects, right? If you try to put your left hand on your right hand, they don't match up exactly correctly. They're very, very distinct from each other. If I were to compare that to something like a square, the mirror image of a square looks exactly like the original object. So we have two identical objects, and because they don't behave like our hands, in other words, the mirror image of the square on the left is exactly the mirror image of the square on the right, we say that they're not chiral because they don't behave like our hands do. So since we're talking about hands, what is it about our hands that made them different from the two squares? Why is it that the mirror image of our left hand, which is our right hand and vice versa, why are those two objects different from each other? Whereas when we took the mirror image of the square, we found out that it was the same object. And let's take a look at gloves, since we are talking about hands. So if I take a look at a pair of gloves that you kind of put on your hand, these disposable gloves, if I were to ask you about this glove over here, does this glove fit on your right hand or on your left hand? Your answer might be, well, it could actually fit on both, right? And you'll be absolutely correct. When you take out a pair of disposable gloves, you can put them in either your left hand or your right hand, doesn't really matter. Whereas, let's say you have a pair of fancier gloves, like, golf gloves or something like that. So if I take a look at this glove over here, this glove has a strap on the one side that's supposed to be facing you when you take a look at, the back of your hand. And if I were to ask you, is this glove going to be made for your right hand or your left hand? Your answer would be, oh, that glove fits on my left hand. Can't fit on my right hand. And that's because the only correct way to wear this glove is for this strap right here is to be facing towards you when you're staring at the back of your hand. What about if I were to ask you for this glove right here? Well, that glove, right, if you sort of orient it in your head, can only also fit on your left hand. Now, what makes a difference between these disposable gloves and the fancier gloves is that the disposable gloves, the ones that can go on either hand, versus the gloves that can only go on a specific hand, have the following difference. And that is that the gloves that are disposable, the front and back of the glove are exactly the same. There is no front and there is no back. If you turn that glove, frontwards and backwards, it looks exactly identical. Whereas you can see with these fancy golf clubs, the reason that we say they fit on only one hand is because, like I said, this strap goes in a very particular place. And this sort of, smoother inside of the glove can only be, inside the palm and not facing towards you. So chirality is all about symmetry. If your object has symmetry, kind of like the two squares that we saw from before, which were symmetrical inside of the object, then there's no chance for chirality. But if you take a look at your hand, the left half of your hand isn't exactly like your right. Like, for example, if I were to take a look at this glove right here, the right half of our hand has a thumb and an index finger, whereas the left half of our hand has a ring finger and a pinky. So they're not identical. And so chirality is all about symmetry. Chiral objects are ones that don't have symmetry, which is why their mirror images are not exactly the same as the original. So how can I make sure that my molecule is chiral or not chiral? Well, if it's chiral, then it needs to avoid symmetry. So in order to avoid symmetry on a molecule and make sure that it is chiral, a molecule has to look different from all angles. So if I were to take a look at ethanol, okay, so this molecule right here, you'll notice that ethanol has a hydrogen towards me. Remember that the wedge means that the atom is coming towards you, and it has a hydrogen away from me on a dash. So because the version of the molecule that's coming towards me is exactly like the one that's going away from me. There's some symmetry there. So the atom that's coming towards me is exactly the same as the atom that's going away from me. And that means that the front and back are the same, so there is no chirality associated with that particular version of ethanol. But if we make a slight change, and let's say that instead of having two hydrogens attached to the same carbon, let's say that I have a different isotope of hydrogen, which is deuterium. So now the atom that's coming towards me is only deuterium. The atom that's going away from me is only, quote unquote, regular hydrogen. Now the front and the back are not the same. And when you do have that lack of symmetry, that means you have a chiral molecule. And so to be able to identify a chiral molecule, there are certain characteristics that we have to take a look at. But before I do that, though, what I want to do is address the possibility of double bonds. So double bonds do offer opportunities for symmetry, and we'll take a look at exactly how that looks like. So let's say that I'm taking a look at this molecule. So this molecule has a fluorine and a methyl group on the left-hand side, and it's got a chlorine and a hydrogen on this side. So you're looking at this molecule, and if I'm asking you, right, you would say exactly the same thing as I told you. The fluorine's on the left at the top there, and the chlorine's on the right. If I were sitting across from you on the other side of this molecule, here's what I would notice, okay? For me, because I'm sitting on the opposite side of you across from the table, the chlorine to you is on the right. To me, the chlorine is on the left. To you, this fluorine atom is on the left. To me, that fluorine atom is on the right. Okay, and the same thing goes for the methyl group and for the hydrogen that are downstairs. And so if I were to just rotate this molecule 180 degrees, right, and that's all I'm doing, I'm not changing anything. If I were to rotate that molecule 180 degrees, this is how it would look like. Okay, so if I just turn it around, and notice there is no difference between the molecule on the left and the molecule on the right. So even, when we're looking at the same molecule, okay, what you notice in front of you is exactly what I notice in front of me as well, right? So your version, looking towards me, or looking towards yourself, is very much the same as the version that I am looking at as well. And that means that the molecule, right, has symmetry. So around that double bond, there is no chirality. So if that's the only thing that's on there, if that's the only functional group on that molecule, then it means that that double bond doesn't introduce any extra symmetry, and that double bond takes chirality out the door. So double bonds are not going to be conducive to chirality at all. So how do we spot chiral centers? And this is the point that I was trying to get to. Well, they have the following properties. You have to have 4 different substituents, because as we saw in the earlier version of ethanol, when we had 2 hydrogen atoms that were identical, that means that there was some symmetry in our molecule, and we can't have symmetry. So we have 4 different substituents, and those must be there in order to have what we call a chiral center. And that goes hand in hand with having sp3 hybridization. So if you're going to have a chiral center, you have to have 4 different substituents, and you got to have 4 different attachments to you. So chiral centers, in terms of nomenclature, are also known as stereocenters. So you may see that terminology. Sometimes they're called stereogenic centers as well, but they're also called asymmetric centers. And hopefully that makes sense, right? Because as we've been discussing, symmetry is not conducive to chirality. And so if we're going to have a chiral center, we can't have symmetry, because otherwise our mirror image would look exactly like the original. So I also wanted to add a little note about chirality when it comes to nitrogen, because nitrogen can be sp3 hybridized, right? But the other thing that we need to make sure of, though, is that that nitrogen has 4 different substituents, and I'll tell you why. And so a lone pair counts technically as an electron group, right? So a nitrogen usually in organic molecules is going to have a lone pair associated with it. But that lone pair allows for inversion. And to show you what I mean, if I take a look at that nitrogen atom, the one with a methyl group attached, and you got 2 different isotopes of hydrogen, those are technically 4 different things attached to that nitrogen. But that nitrogen can kind of flip up and down, kind of like an umbrella blowing in the wind, right? Where the umbrella is supposed to be, its curvature is supposed to be downwards towards you to protect you from the rain. But if it gets really windy, that umbrella can get inverted. So that's kind of the same thing that we're looking at over here, is that lone pair can go up and down, and that inverts your substituents. So long story short, Looking at it from the top is the same as looking at it from the bottom, and that leads to a little bit of symmetry. And so if that nitrogen has a lone pair on it, there's no chirality associated with that nitrogen, although nitrogen can also make a fourth bond. And if it does, and those four substituents are different from each other, well, in that particular case, that nitrogen can be chiral. So if I have a nitrogen with four different substituents attached, then that can lead to chirality.